So from the formula, we can tell a little bit about the chemistry of a certain compound. So for example, acids. Acids have certain characteristics. A lot of naturally occurring acids, like ascorbic acid, they'll have a sour taste to them. Other acids you don't want to taste, but they have other properties, pH properties, neutralization properties, etc. Both words are wrong. But it's actually it was unlocked. And how can you tell we have an acid? Well, an acid is going to have an H. And so it's going to be like HA, where A is just some anion. And so we have an H plus cation. So if we have something like this, that's an acid. We can recognize it as an acid. We also have diprotic acids like H2A, and triprotic acids like H3A. So examples of this would be like HCl. This would be like H2SO4, this would be like H3PO4, phosphoric acid. We also have acid anions like HA minus, like this. This would be a monoprotic, etc. And so we can recognize that this is going to have acidic properties, chemical properties, based on the formula, the composition.
Is there any pertinence to that Wednesday, Thursday?
Oh yeah, I need to make an announcement for this. This is an important announcement because Wednesday and Thursday I have to go out of town for a family business, but I'm looking for a substitute.
No worries. Just post your lectures online. We'll be good.
But I've been looking for a sub for a while now, but nobody can sub at this time. I'm going to check one more person today. But I'll make another announcement tomorrow. But potentially, worst case scenario is if I can't find a sub, I'm going to have to cancel a class Wednesday and Thursday. We'll have to make it up some way. I'll just do that. So let me. During our break, I'm going to go talk to the dean to see if she can fill in for me. If not, then unfortunately I'll have to do that. So anyway, let's continue on with the chemical properties. So chemical properties, acids are like this, and then we start to look, what kind of clues can we get from a chemical formula? So even when we're looking at acids, there's certain acids like HCl versus HNO3. These have quite a bit different properties. So for example, HCl, not only does it have acid properties, but it also has like corrosive properties. That is, it can do what we call oxidize things. And so acids can eat up metals, certain metals. So for example, HCl can eat up aluminum, it can eat up iron, and it can eat through a whole bunch of metals, except it won't eat through copper, it won't eat through silver. HNO3 on the other hand can eat through those metals. It can eat through silver, copper, it attacks silver, which is Ag, copper, which is Cu, etc. HCl will not attack silver. It won't attack copper, but it would attack aluminum, magnesium, some of these other metals here, etc. And so what we want to do is we want to understand, typically when we're thinking about acids, there's certain characteristics of acids that we want to think about. But in general, when we're thinking about chemical properties, we want to figure out some of the chemical properties based on the composition and the structure. Okay, so thinking about types of chemical reactions, we could classify, for example, this, nitric acid, HNO3, reacts with silver. That's one reaction. And then another reaction, nitric acid reacts with copper. And then what we can do is we can take a whole bunch of metals. We try different metals and mix it with nitric acid one by one and see what happens. But is that an effective way of doing this? No, it's not very effective. What we'd like to do is we'd like to group, certain categories of metals, certain types of metals, or certain types of, this is chemical reactions and properties here, props for properties. And so if you think about the number of chemical reactions that occur in nature, do we want to go through those one by one? No, what we want to do is we want to come up with some kind of similarities or some kind of categories, or in other words, we want to look for patterns in chemical reactivity. And it's huge. Therefore, we want to study the patterns in chemical reactivities. We don't want to do memorization of all the observations, which would be innumerable. And so what are the patterns in chemical reactivity? Well, the patterns of chemical reactivity depend on what book you're looking at, and how they subcategorize it. Well, we are going to divide it into three main types of reactions. And we'll look at these individually. The first type of reaction is going to be what we call metathesis. All metathesis is, let me give you an example of it, is just kind of a swapping. So for example, if we're looking at let's say silver, do you know the name of this? Silver nitrate. So if we look at a silver nitrate, and if I write AQ here, AQ stands for aqueous. Aqueous means it's dissolved in water. Silver nitrate dissolves easily in water to form an aqueous solution or mixture with water here. And I think silver nitrate and react it with some HCl. HCl is called what? This is also dissolved in water. This is hydrochloric acid. Then I get a reaction. Now, when we think about HCl, HCl is an acid. And acids have certain properties, but HCl has more than just acid properties. Typically, when you attack metals, you can kind of think of that as acids. But normally, when people think about acids, they think about low pH. Low pH. High pH substances are called alkaline substances, or alkali substances, or basic substances. And so most people, when they think about an acid, they think about a base. They're going to attack a base. But it turns out acids have three types properties. One type is this, metathesis. So HCl can undergo something called metathesis, in which all we do is we swap the ions. So for example, we'll take the silver cation and have that with the chloride anion. And then we'll take the hydrogen cation and place that with the nitrate anion. And so we just swap partners here. That's a metathesis reaction. It turns out that silver and chloride really like each other. They like each other so much that they do what's called a precipitation, and they build up a crystal lattice. And so the ions will start to build a lattice. Versus when the ions are dissolved in water, when the ions are dissolved in water, they're kind of separate from each other. So what happens is these ions come together to form this lattice. This lattice we call a precipitate. Because what happens is we'll start to form a cloudy solid in the solution. And this is aqueous this would be an example of metathesis reaction in which we just swap the ions. So this is type 1 of the reactions. And so we look, when we're looking at chemical properties, all these can have potential metathesis reactions if we just swap the anions and cations and see what happens, right? That's one thing. The next type of reaction is our standard acid-base reaction. And a base is like kind of the anti-acid. And basically, we're going to look at something called a Bronsted acid-base. Bronsted. This is about to die. A Bronsted defined an acid as an H+ donor and a base as an H+ acceptor. So an example of this would be here, if we take HCl plus, this is a common base. Do you know what this is called? The name of it? NaOH. Sodium hydroxide. This is drain cleaner or lye. And this is comparable to an acid-base reaction because what happens is the acid here is the H+, and the base here is the OH-. And so the H+ likes OH-. So what happens is this could be thought of as metathesis as well. The hydroxide going with the H+. When the hydroxide goes with the H+, will form H2O, an H and an OH. And then the sodium goes with the chloride. And so, in a way, this is both. This is both a Bronsted and a metathesis. Now, H2O is what we call a liquid, because if water dissolved in water just sounds funny. So we'll just call it liquid. And then sodium chloride. And so what we do is, this is called a neutralization reaction. An acid-base neutralization reaction, because we're starting off with a pretty strong acid, hydrochloric acid, and pretty strong base, sodium hydroxide, which is a drain cleaner. And all we're doing is we're forming sodium chloride, which is this table salt in water. And so we've completely neutralized this reaction. So this is called a neutralization. Sometimes it doesn't go all the way neutral, but it just becomes more neutral. So this is an example. This is also a metathesis in this case. But it doesn't have to be a metathesis. We could have acid-base reactions that do not resemble metathesis. So let me give you one more example of an acid-base reaction that doesn't resemble metathesis. So another example is we can neutralize hydrochloric acid with ammonia, aqueous ammonia. And when we do that, it turns out that HCl is the proton donor and then ammonia is the proton acceptor. And what we end up forming is ammonium chloride. And so here the H+ gets donated to this. And then we form the ammonium ion. So in other words, the H+ attaches to the NH3 to form NH4+. The chloride, nothing happens to the chloride, so the chloride's still around. The chloride's still around, and it's ammonium with chloride. That's how we end up with ammonium chloride. So that's an example of an acid-base reaction. The next type of reaction is reaction type 3. Reaction type 3 is called a redox reaction. Redox stands for oxidation and reduction. When something's oxidized, what happens is it loses electrons. So let me just do it with an example to show you here. If I take sodium metal and react that with chlorine gas, I will form sodium chloride. Now, this is not balanced necessarily here. And so in order to balance it, I need to change either the coefficients here or something. The easiest is just to change, for every Cl2, I'll need 2 sodiums, and I'm going to form 2 NaCls. And so essentially what happens here is this. The sodium goes from a 0 charge to sodium plus. In order to go from a 0 charge to a positive charge, it has to lose an electron. This electron is going to be the negative charge there. And that means a chlorine. So what we'll do is we'll take the Cl2 molecule and we'll break it up into atoms. So we'll dissociate. This is called dissociator. Very bond here. Dissociate this. So we have a Cl. Now the Cl is going to gain an electron to form Cl with a negative charge. So we're going to end up with Cl minus. And so what we say is this. We say that sodium was oxidized. And that chlorine was reduced. Now, the nomenclature part of this gets very tricky because sodium was oxidized by who? Sodium was oxidized by, well, where did the electron end up going? Sodium was oxidized by who? By, in this particular reaction, it's going to be by chlorine. So the sodium was oxidized by chlorine. In this case, Cl2. We call chlorine the oxidizer.